a long time ago, when I started teaching astronomy, there were maybe one or two planets known to be orbiting stars other than the sun, and they had been discovered in the mid-90s, early 90s. Okay, the data was still quite fuzzy, but there were a couple. It was very exciting. Today, we have, as of today, I checked the NASA Exoplanet website, and as of today, we have 4,164 confirmed exoplanets. And of course, an exoplanet is simply any planet that orbits a star other than our own sun. 4,164 confirmed, 5,220 candidates. That is things that we are really pretty sure are exoplanets, but we don't have the periods figured out, the orbit time. Not until we get that piece of information is it confirmed. But we're pretty sure about 5,220 candidates. And these 4,164 confirmed exoplanets are orbiting in 3,085 different systems. 3,085 systems. That is distinct systems of planets around distinct stars. So that means we know of 4,164 confirmed exoplanets orbiting 3,085 different stars. So many of those stars have more than one known planet around them. Most of them probably only have one, but a large minority, 40-45% of them, have more than one. Okay? And in fact, there's two of them that are known to have 7 planets orbiting them. Okay? So we have had in the last 20-30 years a real explosion. In fact, 30 years ago, there were no other planets known anywhere except for our own. 25 years ago, when I started teaching, there were a couple that were kind of known. And today, there's 4,164 that are well known. Why did it take so long? Well, because it's hard. Because stars are really far away. Okay, you think the planets are far, you think Jupiter's far away, you think Neptune's far away, you think the Oort cloud is far away. I mean, nothing compared to the closest star. So detecting planets on other stars is really hard. We have probably a half dozen ways of doing it now. I'm going to mention 3 of them to you. That is how we detect them. Okay. The first method, 3 ways of detecting exoplanets. The first one we're going to call radial velocity. This is how the first ones were discovered. In other words, not until very recently have we discovered exoplanets by looking at them. Okay. It's kind of like if you go onto an island somewhere and you see tiger tracks, you haven't seen the tiger, but you know there's a tiger there, right? You know you need to be careful because there's a tiger there. Have you seen the tiger? No, but the tiger leaves a trail. Tigers leave marks. You know tiger marks when you see one. Same kind of deal with exoplanets. Not until very recently, last 5-7 years, have we ever even gotten an image of an exoplanet. But there are telltale signs of them. Okay. So let's look at an orbit of a star. Okay. Let's see. Here is a star. Actually, let me make the star look like a star so we can keep the planet and the star distinct. Okay. So here's a star, and here's its planet. Okay. They're orbiting the center of mass. So if we're over here, okay, this is us, That's our eyeball looking this way. If we're over here, the planet and star are orbiting at the same center of mass. If the star is orbiting, the planet's going this way around its orbit, and the star is coming towards us around the center of mass. Right, because the star's orbit looks like this around the center of mass, and the planet orbit looks like this around the center of mass. Remember, Jupiter doesn't orbit the sun. Jupiter and the sun orbit their common center of mass. So here's the star moving towards us. Here's the planet moving away from us as they orbit their common center of mass, which is right in the middle. Okay. Half an orbit later, the star's down here. The planet's down here moving towards us, and the star's up here moving away from us. Okay. So they orbit their common center of mass. So what basically happens is this. The star, which is the only thing we can see. We are here. This is us on Earth. The only thing bright enough for us to see is the star. Okay. We don't see the planet. But what we see the star doing is moving towards us, then away from us, and towards us, and away from us as it wobbles and the planet slings around it. Remember, we talked about the sun's 12-year wobble. As Jupiter orbits the sun's got a little 12-year wobble it does, a little dance it does, which means sometimes it's moving one way, sometimes it's moving the other way. As we watch this, sometimes the star is approaching us, sometimes it's moving away from us. We can detect that motion towards us and away from us because the light from it changes a little bit. When it's moving towards us, the light is said to be blue shifted. When it's moving away from us, the light is said to be red shifted. Okay? The light changes color a little bit as it moves toward. If I take a white flashlight, or if I take a green flashlight and run towards you, it will look blue to you if I run fast enough. If I take a green flashlight and run away from you, it will look red to you. There's a small color change in color of the light as the star moves towards and away from us. That's how we detected the first exoplanets, by looking at the way that the starlight changed color as it wobbled towards and away and towards and away from us. That's the radial velocity method. Okay? By looking at the way the star's color changed. Now we can't see with our eyes, but with really good equipment, something called a spectrograph, we can see the color of a star change as it moves slowly towards us and away from us. In that wobble, towards, away, as it's being slung around its common center of mass with the planet that we are looking for. Okay. Again, we don't see the planet, but we see the effects of the planet on the star. We don't see the tiger, we see the tiger tracks. We don't see the planet, we see the effects of the planet on the star. We don't see the planet, we see the star's color change as it wobbles due to the planet's presence. Clever, huh? Well, it works. The second one is known as a planetary transit. Now, we've seen transits before. A transit, remember, is like, say, when Mercury or Venus passes across the disk of the sun from our perspective. So, if you imagine looking at a star, say this is the star, the face of the star. Okay. As a planet passes in front of it, if we are aligned such that the planet eclipses the star, or rather occults the star, or transits, it's going to pass in front of the star. Just like Venus passes between us and the sun. So this is 1, 2, 3. If we then look at the brightness of the star as a function of time, we will see the brightness of that star do this. It will be high, then it will dip a little bit, then it will go up again. It will dip during part 2, because when the planet is in front of the star, that little bit of the star's face, we don't get light from it anymore. The overall brightness of the star, the intensity is the actual word for it. This is intensity. This is time. Right, always label axes. That's one of the, I need to follow my own rules. Label the axes. So before the planet transits, the star is bright at 1. When the planet is passing the face of the star looks dimmer because part of the face of the star is blocked from us by the planet, so it drops in brightness. And then when the planet leaves, it goes up again. And we see this happen as the planet orbits the star over and over and over again. We see this happen over and over and over and over, and we can predict it perfectly. This is another way of detecting an exoplanet. Okay, the third way, by the way, this orange curve here, the brightness, the intensity versus time, that's known as a light curve. So the light curve of the star has a regular and periodic drop as the planet passes in front of it. And this only works in those cases where we are edge on with the planet orbit. Right? If we're looking face on to the orbit and the planet's going around this way, we don't never see this happen. Only when the orbit of the planet is in the plane of the Earth from our point of view. When we're looking edge on at the star system, at the planet system, only then can we see a transit. So this happens in a minority of cases, but we get some of the best data this way. The third way is direct imaging, which is, like I said, a fairly new way of doing it. There's a really nice direct image. If you look on page 369, figure what? Figure 15.5 shows a really nice direct image of a planetary system other than our own. The difficulty here is immense. The difficulty of detecting a planet, it's like this. Imagine, imagine there's a bug flying around a street light. You've seen this 100 times in your life, right? Now suppose you're 50 miles away from that street light and you want to take a picture of the bug. Not the street light. You want to take a picture of the bug. That's hard to do. You got to block out the light from the street light itself and hope to see the little bug reflecting the light from the street light. But it's hard to do. It's like trying to take a picture of a bug buzzing around the street light from 50 miles away. Okay? Hard to do. Yet we have been able to do it. So that's the third way. There are other ways. Gravitational microlensing. That's a big mouthful. That's a fourth way, but there are a couple other ways as well. But these are the three big ways: radial velocity method, planetary transits, and direct imaging. That's how we've built up most of these 4,164 confirmed exoplanets. That number will be different by the time you watch this video. Next up, we're going to talk about the planets that we've actually found this way and compare them to planets in our own solar system. See you then.